welcome back, everybody. Yours truly, Brandon Steckler, Technical Editor of Motor Age Magazine, back for another episode of Mastering Diagnostics. And this episode is regarding automotive HVAC systems, particularly a device that many still are not familiar with, known simply as the IHX. IHX is an acronym standing for Internal Heat Exchanger. And basically, the job of this device is to help optimize the functionality of the modern HVAC system. What I mean by that is how heat is exchanged. And we're going to get into the nitty-gritty details of automotive HVAC systems in particular, and of course at a level that's attainable and usable for us as automotive diagnosticians. So not necessarily at an engineering level, because that's beyond my capability. But I certainly want to keep things applicable. So I want to begin by talking about emission standards, because as you know, everything you or I do on a daily basis, in some way, shape, or form, relates to emissions standards. Now, going back to when I was a youngster, back before the early 90s, there was a change that occurred in refrigerant that we used in the automotive systems. And the original refrigerant that was used for decades was known brand name as Freon, but chemically as refrigerant R12. Now, R12 performed very well as an automotive refrigerant. In other words, how it absorbed and gave up heat served us very well in the climates we experience here on Earth. And that made it a very good refrigerant to use in the automotive HVAC systems because it did such a good job. But as you know, that refrigerant was found to have put holes in the ozone layer, depleted that layer of protection that surrounds the Earth and prevents harmful UV rays from doing damage to us and the world around us. So there became a need to transition into a refrigerant that didn't have that ozone depleting characteristic. And of course, research was performed and lots of experimentation by chemists, and they settled on a refrigerant known as R134a. And if you were around at the time that R12 and R134a was being leveraged, we performed a procedure called a retrofit where we converted, if you will, the systems that leveraged R12 usage. We now gave them the ability to use R134a as a refrigerant. And there were some changes that had to occur using different types of refrigerant oil, the oil that's designed to lubricate the compressor, simply because the R134a, the new refrigerant, would not carry the original mineral oil that R12 would carry, almost like a backpack. So they reformulated and used a different type of oil that the R134a would carry to lubricate the compressor. And since I'll say the mid 90s, early to mid 90s, we leveraged R134a and it worked very, very well. It works well now. But the original R12 was known as a gas with a characteristic called a CFC, or a chlorofluorocarbon, and that is what depleted the ozone layer. So moving from a CFC like R12 to R134a, this now possessed a characteristic known as an HFC, or a hydrofluorocarbon. And again, it worked very well, not quite as well as R12, but good enough to do the job we needed it to do. And it eliminated, or at least reduced, that potential for damaging the ozone layer. But as time goes by, emission standards got more and more stringent, and we now became aware of the fact that the temperature of the Earth was increasing, what we know as global warming. And there are many different contributors to global warming factors, but one of which found within the automotive HVAC systems is the fact that the HFC, or hydrofluorocarbon, known as R134a, contributed to global warming. So studies have been shown that R134a is now a greenhouse gas, and we cannot maintain the emission standards we set by using R134a long-term from this point moving forward. So we needed another alternative. Now, this is where the governing bodies have found what we know as a global warming potential. So, and global warming potential is a measure of how much greenhouse gas in the atmosphere over a specific time, all relative to carbon dioxide, meaning that's the point of reference. So, carbon dioxide has a global warming potential of 1. Every other gas being compared to it is done so by a multiplicative factor. So, a refrigerant like R134a has a global warming potential of 1430, whereas new refrigerant we're using now, R1234yf, has a global warming potential of only 4. So it makes it tremendously valuable in an effort to reduce the contribution of emissions leading to global warming potential. So this is where the introduction of R1234yf came to be. And what's great about 1234yf is regarding from the technician's standpoint, there is not much variation in how it works within the automotive systems. There are a few changes, like the potential for a fire hazard to occur, but it's still very minimal at best. So my point is how you or I, as a technician, approach a 1234yf system diagnostically is still very similar to that of a R134a system, meaning we're already familiar with it. So that's some of the good news. Now, apples to apples comparison, 1234yf does not cool as well as R134a. And with that, some systems implement countermeasures to overcome this lack of performance naturally. And this is where the IHX comes into play. The goal of the IHX is to simply boost or optimize system performance by maximizing heat transfer. But we're going to talk about that in some detail and how it's applicable to automotive diagnostics for us as technicians. So before we move on, I want to take a step back and, as usual, discuss things at their most basic operating characteristics, specifically the operation of the refrigerant loop. In other words, how AC systems truly function, the heat exchange that takes place. So the first two concepts I want to bring up is something known as sensible heat and latent heat. And as it sounds, sensible heat is the heat we sense. Now, let me back up 1 minute and mention thermodynamics. It's the exchange of heat energy that allows the HVAC systems to do what they do. And a very important concept to mention is thermal energy and its unit of measure. In other words, a BTU, or British thermal unit. British thermal unit is a measurement of heat energy, how much energy it takes to raise the temperature of a pound of water by 1 degree Fahrenheit. That would be 1 British thermal unit. So how does that relate to what we know as sensible heat? When we take British thermal units and we add it to, let's say, water, let's say in a pot on a stove, it takes 180 BTUs to take water at 32 degrees Fahrenheit and bring it up to 212 degrees Fahrenheit. That's the sensible heat. That is something you and I can measure with a thermometer. So 180 British thermal units takes virtually ice cold water just above freezing all the way up to the point where it's going to boil. Only 180 British thermal units, or BTUs. So that's sensible heat. And again, that's something you and I can see with a thermometer. But here's where some magic happens. When liquid water at 212 degrees Fahrenheit goes from a liquid to a gas, we know that as evaporation, some almost magic takes place. Again, it only took 180 BTUs to take ice cold water all the way up to the point that it's boiling. But to take it from liquid to a vapor, in other words, when it actually boils off, takes an additional, not 180, but 970 BTUs of thermal energy. to get that process of evaporation to occur. And this is where the magic of the HVAC system comes into play. So the first discussion point I had was taking liquid water from 32 degrees Fahrenheit to liquid water, 212 degrees Fahrenheit. That is sensible heat. We can measure that with a thermometer. And although we add another 970 BTUs from liquid water to change it to a vapor, your sensible heat will not change. You will not notice any change on a thermometer. So it's the change from a liquid to a vapor and from a vapor to a liquid that allows this tremendous amount of heat energy to be moved. When we move heat energy into a liquid, it becomes a vapor. When we move heat energy out of a vapor, it becomes a liquid. And that tremendous movement of energy is what we sense, what we can feel on our skin as cold air being blown into the cabin. Technically, it's not cold air. It's air that lacks energy. And it's the heat transfer from our body to the air that allows us to feel a sense of comfort. So let's talk about how this applies to the automotive refrigerant loop or the components that make up our HVAC system. What we have here is just a generic drawing that I've put together, a simplified drawing, if you will, that generally represents a cycling clutch orifice tube system. Now, of course, not all the components of the HVAC system are demonstrated here. However, there's enough to get the point across. So we have our AC compressor that circulates the refrigerant. And what we first do is we use the compressor to discharge or circulate the refrigerant. Now it leaves the compressor as a pressurized, hot, high pressure gas. And that's why I have it colored in red here. Now, as the hot, high pressure gas leaves the compressor, it heads out to the front of the vehicle where air is blown across the condenser fins. And through that process of convection, the heat energy inside the refrigerant is transferred to the air blowing across the AC condenser. So the hot, high pressure gas that leaves the AC compressor becomes a hot, high pressure liquid. Why? The heat energy exchange, the British thermal units that were moved out of the vaporized refrigerant, allow the refrigerant within the condenser to become condensed or liquefied. So it is still hot, it is still under high pressure, and it is now in a liquid state. And again, the importance of that is because it's evaporation that is going to allow the heat exchange to produce a cooling effect. So stick with me here. So this hot, now high-pressure liquid makes its way across, at least in this system, a restriction known as an orifice tube, a fixed restriction. So just like voltage drop in a circuit when you have current flowing across a resistor, when we have refrigerant flowing across a restriction, there will be a noticeable pressure drop. So this now hot, high-pressure liquid being represented in orange becomes a cold, low pressure liquid. And as this low pressure liquid makes its way into the evaporator, another heat exchanger, just like the condenser, the heat energy, or BTUs, if you will, inside the cabin where you and I reside, will be transferred into the liquid refrigerant. And as this liquid refrigerant takes on the BTUs from the cabin, the liquid will evaporate in the evaporator and become a cool, low pressure gas. Technically, it's a little bit liquefied and a little bit gas, but it's more a gas. As it makes its way back to the compressor squeezes the cool, low pressure gas and makes it a hot, high pressure gas, and the process repeats itself again. Now, again, this is nothing more than a generic drawing of an orifice tube system. And just for good measure, I will show a picture of an expansion valve system. The process is very similar, but the configuration is a bit different. So instead of having a fixed restriction here, we have a variable restriction here. And this is usually coupled with a variable displacement compressor in many configurations. But the compressor discharges the pressurized gaseous refrigerant across the condenser, where it sheds BTUs or heat energy to the air through the process of convection. And the now liquefied, hot, high pressure refrigerant collects and is stored here in this receiver as liquid, because the throttling of the expansion valve will allow more or less refrigerant to pass through the evaporator depending on heat load. But the process functions very similarly. The process of evaporation and condensation occurs very similarly in the expansion valve system as does the orifice tube system. So being able to transition away from a cycling clutch orifice tube system to a variable displacement compressor coupled with an expansion valve system means now we can control how much refrigerant is being circulated in the automotive refrigerant loop. And being able to reduce the amount of circulating refrigerant takes the mechanical load off the compressor. Now, if you take that a step further, because the compressor is typically engine driven via a serpentine belt, the mechanical load that we've taken off the compressor now takes the mechanical load off the engine. And of course, you can easily see how that will reduce tailpipe emissions and simultaneously boost miles per gallon fuel efficiency. And with that, as time goes by, the size of the refrigerant loops, meaning the amount of capacity, the amount of refrigerant these refrigerant loops hold, is significantly less than in years past. In other words, back in the days of R12, we had tremendous refrigerant loops that held 2 pounds or more of R12, whereas today's system holds a fraction of a pound. And the significance of me telling you that is this. In the days of old, with a loss of refrigerant, we could still have relatively decent performance as time goes by. However, with today's refrigerant loops, even a slight loss in refrigerant can cause a tremendous decrease in HVAC performance and customer satisfaction. And with the reduction of the amount of refrigerant in today's loops, it's even more important that the efficiency of the system is where it needs to be, because after all, it's the refrigerant that allows for that heat absorbing or heat transferring ability. And when we have a system that lacks refrigerant, the ability for that refrigerant to pull heat load out of the cabin is reduced simply due to the fact that there's less refrigerant in the system, meaning these systems have to work more efficiently than ever before. So to describe what I was trying to tell you a moment ago, if we had frozen water, in other words, a solid here, as we continue to increase temperature, sensible heat, in other words, something we can measure with a thermometer, begins to increase here. Now, of course, this is degrees Celsius, but degrees Fahrenheit would reflect similarly as far as trend of the graph goes. So noticeable temperature change, again, temperature change is occurring within the water itself. However, at the point that the solid ice becomes liquid water, even though BTUs are continuing to transfer into the ice, or I should say into the water, the noticeable temperature change is not taking place. There is no change in sensible heat, just latent heat. But as soon as the solid water becomes liquid water, in other words, the ice becomes water, sensible heat will once again begin to rise as we continue to pump more and more BTUs into that water. And it will continue to rise to the point that the water starts to boil, which would be about 100 degrees Celsius or 212 degrees Fahrenheit. But once again, since we are changing states, the liquid water, although it is turning into a gas, its sensible heat, what we measure with a thermometer, is not changing. And after that liquid becomes a fully saturated gas, temperature continues to increase. And that's what we see happening right here. So mentioning the fact that R1234YF is not as efficient naturally as R134a. The systems, apples to apples comparison, simply don't work as well as the R134a systems do. Again, apples to apples comparison. So many vehicles nowadays leverage a component to help boost efficiency. And that component is known as the IHX, or internal heat exchanger. So this is a picture of an internal heat exchanger. And basically this looks like a refrigerant pipe, and that's exactly what it is. But what you can't see here, it looks like a Siamese pipe. And what we'll notice here, if we look at the large diameter pipe, this represents basically the suction hose, the hose that leads from the heat exchanger inside the car, the evaporator, out to the compressor assembly. And this little hose of the Siamese hose looks like a high side hose or a liquid line leaving the condenser and making its way back up to the evaporator on the inlet side, or the expansion valve on the inlet side. But these two Siamese pipes are impregnated within one another. And if you were to cut one apart, it would look something like this. You'd have the low side portion of the hose on the inside and the high side portion of the hose on the outside. Now, what's the purpose of us doing this? It's two different processes, one known as superheat and the other one known as subcooling. So let's talk about that for a moment. So as you can see here, subcooling is condensation that occurs when a vapor loses heat and turns into a liquid. But subcooling is when that liquid is cooled below the temperature at which it turns into a liquid. So what I mean by this, as pressurized, hot, high-pressure gas leaves the compressor and heads through the condenser, it sheds its heat, right, British thermal units, to the air, to the atmosphere that blows across those condenser fins through that process of convection. When the gas or the gaseous refrigerant becomes liquefied refrigerant, that's condensation. However, when that temperature of that liquid refrigerant begins to drop afterwards, that is known as subcooling. So basically, subcooling is any amount of cooling that takes place to the liquid refrigerant after gas becomes liquid. Gas becomes a liquid, we call that condensation. Any additional heat loss is known as subcooling. And you can take a guess what superheat is. Boiling is when a liquid gains heat and transfers into a vapor. Of course, we've been discussing that all along. Superheat occurs when the vapor is heated above its boiling point. So when we were to take liquid refrigerant and push it across the evaporator, and the evaporator allows BTUs from within the cabin to get transferred into the refrigerant, that refrigerant is going to boil. Once it becomes a gas, it's fully saturated. However, when that gas begins to increase in sensible heat that we measure with a thermometer, any sensible heat added to that gaseous refrigerant is known as superheat. So why is this important? It's important for two reasons. For one, on the subcooling side, we are adding additional heat absorption capacity to the refrigerant. So if I take that gaseous refrigerant and I turn it into a liquid, in other words, I condense it, and then I remove additional British thermal units from it, I've given more capacity, more ability for that refrigerant to absorb heat. And of course, you can see how that could boost efficiency in the operation of the automotive refrigerant loop. But where does superheating come into play? Here's what can happen that could be detrimental to an HVAC system, and we're going to talk about how superheat can prevent that from occurring. Particularly on an expansion valve system like this, where refrigerant is throttled. It's not only metered here across an internal restriction, but it's throttled, meaning we can open up the throttle of the expansion valve and let more liquid refrigerant flow through the evaporator. Or we can close this and throttle down the circulation of refrigerant and reduce the amount of flow through the evaporator. And that's the purpose of the receiver. When we reduce throttling through the expansion valve, this receiver will begin to collect more liquid refrigerant as it leaves the condenser. When we open up the throttle of the expansion valve, this receiver or reservoir, if you will begin to drain and let more refrigerant circulate through the evaporator. Again, the reason being is, as we discussed earlier, if we don't make the HVAC system work any harder than it has to, it allows for efficiency. Again, miles per gallon. But here's what happens under full throttling of this expansion valve, where liquid refrigerant is allowed to circulate at its highest rate through this evaporator. If the cold liquefied refrigerant entering the evaporator does not fully evaporate or become a saturated gas, liquid refrigerant will enter the compressor. And just like in an engine, we cannot squeeze a liquid. A hydrolock situation will occur, and this is when connecting rods and such get bent, and this could cause significant damage to the compressor when what we call slugging occurs, when that compressor inhales or ingests liquefied refrigerant. So the significance of the IHX, as far as on the low side goes, when refrigerant leaves the evaporator and heads back through this low side, what we call suction pipe. Internal here, it's running parallel to the very hot high side gases. And the heat from the high side is allowed to be exchanged to the low side. And what will that do? That will ensure superheat occurs and boils off any liquefied refrigerant, preventing liquid refrigerant from making its way to the compressor. So now comes the fun part of mastering diagnostics, and that's leveraging the science, because the science is something we can put our hands on. And if we can learn to leverage the science, our job as automotive diagnosticians becomes less and less stressful and more fun. So I have a really close friend. He's like a brother to me in the automotive industry. He's an industry leader, one of the best diagnosticians on the planet, and works hand in hand very closely with automotive refrigerant engineers. We're talking about thermodynamics. He's taught me how to leverage something typically used at the engineering level that could also serve as a diagnostic tool for us as technicians. Now, this enthalpy chart you see here, again, is a tool not typically used at the automotive diagnostician level. This is more on the engineering side of things when they are designing refrigerant loops and monitoring how thermodynamics occur within an automotive refrigerant loop. What we have here is known as a bell curve. And this bell curve defines the boundaries in which, in this case, R134a turns from a liquid into a gas. So let me start off by saying everything to the left of the bell curve here represents refrigerant in a liquefied state. And everything to the right side of this bell curve represents refrigerant in a gaseous state. Now, these green lines here, you and I are not going to use as they're intended to be used. These represent entropy, okay? But you and I are simply going to use them as basically like a ruler to give us a straight line, something that runs parallel to our bell curve. Now, what I want you to notice is this. In blue is our temperature designations, and every blue line represents a change in temperature of 20 degrees Fahrenheit. So as we make our way to the right of this chart, it's showing an increase in temperature. And if we make our way towards the left of the chart, it's a decrease in temperature. Now, I want you to notice the significance about the temperature from left to right as we enter the bell curve. Watch this. We go from minus 60 to minus 40 to minus 20 to 0 to 20 degrees Fahrenheit. And then once we enter the bell curve, temperature stays exactly the same. And as soon as we exit the bell curve, temperature begins to increase by 20 degrees once again. And this occurs no matter where you are in this bell curve. The significance is this chart is showing refrigerant changing from a liquid to a gas. And as we talked about at the beginning of this video, liquid refrigerant increasing in sensible heat is what's happening here. Once the liquid refrigerant becomes of a certain temperature and begins to boil, as it changes state, sensible heat temperature remains exactly the same. And as soon as we become a fully saturated gas, temperature of the gas will begin to increase again in this superheat region right here. And on the flip side, temperature will begin to decrease in the subcooling region right here. So we are going to be able to plot information that will give us this geometric shape here to show us visibly thermodynamics occurring within the refrigerant loop. And the significance is where these lines are plotted and how they intersect each other, relative to this bell curve. This really holds significance to the operation of the HVAC system and its performance evaluation, if you will. In other words, we can look at this and get a visual interpretation of how well the refrigerant loop is doing its job, or how hard it's working to do its job, or if it's not doing its job properly at all. And we can do that without the typical approach to HVAC diagnostics. In other words, we don't have to evacuate and recharge a system as an experimental step to see if it's properly charged. We can yield the information from this data, that these plotted data points here, to give us some insight onto system performance. In other words, we are seeing the energy in this closed loop refrigerant system as heat is exchanged both in and out of the climate around us. In other words, as heat enters the system or exits the system, it's going to produce a significant point on this chart, and where they all intersect represents the functionality of this system. So the first thing you have to keep in mind here is pressure here shown vertically on the left side of this chart. It's drawn here in pounds per square inch, but what you need to know is this is represented in absolute pressure. So if we are reading a gauge and it reads 0 psi, and for instance, I was at sea level, I would have to add approximately 14 to 15 pounds to my reading. So if I had gauge pressure, I'd have to draw on the chart an additional 15 pounds. Again, just something you need to keep in mind. As I mentioned earlier, the numbers on the bottom of the scale are something we're not going to use. That's entropy. But we are going to use these green lines that are radiating outwards from these green numbers here to act as a visual point of reference. So in order for this chart to serve its purpose for us as diagnosticians, there's just basically 4 pieces of information we need to know from the system we are evaluating, so we can plot this information on the chart and have it build a model, if you will, of visual thermodynamics of system performance. So we need to know the high side pressure, again, in absolute value. We need to know the low side pressure, so we gain that from our manifold gauge set. We will need to measure temperature, specifically at the compressor inlet, and temperature just before the metering device, like that of the orifice tube. Now, it's not to say that this evaluation technique cannot be applied to an expansion valve system, but what makes it difficult is this technique to be applied to those systems is the expansion valve is typically inaccessible, meaning we can't measure temperature on the inlet to the expansion valve accurately. We'd have to do so further away from it. So this doesn't work as well on those type systems, but the technique does in fact work. So what we see here is what we've grown to expect from normal operation. And as you can see by plotting these lines that I'm about to describe to you shortly, is this geometric shape falls very close to the perimeter of this bell curve. So this would be where refrigerant enters the compressor. This is refrigerant being pressurized as it leaves the compressor. This is the refrigerant coming across the condenser and giving up its heat to become a liquid. And then as it becomes a liquid, a very minor amount of subcooling takes place, and we cross the restriction of the orifice tube. There's a tremendous pressure, therefore temperature drop. And as the liquid refrigerant crosses the evaporator and becomes a gas, it absorbs heat, but again, the temperature doesn't increase because of that change in state, and we start the process over again. What can be seen here as a normal characteristic is the temperature in which we come across the evaporator. We can see is just above freezing, which is desirable for yielding us those cool cabin temperatures. We have a little bit of superheating take place, which is what we need to prevent liquid refrigerant from slugging the compressor, if you recall from earlier in the video. And these temperature lines we have here, I have highlighted in blue showing the two temperature lines to the right of the chart. Typically, you will see this point here, our high side pressure, stay darn close to this, indicating a little bit of superheat, but not too much. This is what we call desirable and expected proper operation of a refrigerant loop. So this is an instruction on how to plot the information. So this very first point you see here in the lower right portion of this graph represents the inlet temperature and pressure. In other words, pressure on the low side entering the compressor and the correlating temperature. The temperature with our temperature probes is at about just above freezing, and our pressure is just above 42 psi, give or take. Now from there, we plot our point and we draw a line projecting outwards parallel to this green line right here. This next point here represents temperature just before the metering device. So this is about 120 degrees Fahrenheit shown here. And high side pressure as well, just below 200 psi. So this line will be carried out straight to the right to intersect this line here, and it will drop straight down as well. The horizontal line represents the energy exchange at a fixed temperature across the bell curve as we cross the condenser and shed heat. And this is the pressure drop across the restriction of the orifice tube. So again, this lower line representing temperature across the evaporator, and this is where the gas enters the compressor, is squeezed and compressed to build pressure. This is the energy exchange, the heat exchange across the condenser as we shed heat and become liquid. This is showing a saturated liquid outside of the bell curve, and our pressure drop across the restriction of the orifice tube, yielding us a drop in temperature, which is reducing the temperature of the liquid gases entering the evaporator. Here they are taking on heat energy to become a fully saturated gas outside of this bell curve with just a little bit of superheat, so the process repeats itself. If this line plotted fell too far within this bell curve, it would still be liquefied and we could slug the compressor. So again, the superheat, anything above or to the right of this black bell curve indicates superheat, and that's desirable. We need some superheat to ensure that the refrigerant remains in a gaseous state when it feeds the compressor. Once the temperature of the refrigerant sheds 20 to 30 degrees Fahrenheit here of superheat, it will then begin to change states from a gas to a liquid, and that's exactly what we're witnessing right here. Because it's to the left of the bell curve here, it's proving it's a saturated, fully saturated liquid, which is desirable because we need the liquid refrigerant as such so it can evaporate and absorb heat. If it stays within this bell curve, it is not yet a liquid, meaning it doesn't have the ability to absorb as much heat, as much BTUs as it would if it was a fully saturated liquid. So that's what we should expect to see from a healthy system. And again, the significance is where that geometric shape falls relative to that bell curve. It barely extends outside the bell curve to the right, indicating superheat is taking place, but not an excessive amount. And it barely hangs outside to the left of the bell curve, indicating a fully saturated liquid occurs, giving us that heat absorbing capacity to pull heat out of the cabin. Now we're going to start introducing different faults. And the significance is we're going to be able to see the faults on the chart as it's plotted against the bell curve to help us make some diagnostic decisions without having to remove refrigerant as an experiment or add refrigerant as an experiment. So in this example of a low charge system, first and foremost, the system is performing as it should. In other words, the refrigerant is doing its job. But since we are low on capacity, even though the refrigerant temperature of the refrigerant entering the evaporator is below freezing, there's such a small amount of it, it can't absorb the heat out of the cabin efficiently. So temperature is below freezing at this point in time entering the evaporator, and it's changing states from a liquid to a gas. And because the heat in the cabin has to enter or transfer into only a minor amount of refrigerant, it takes on more heat load, and this is where superheat takes place. So as you can see, the temperature as the refrigerant enters the compressor is increased. As the compressor outputs the compressed refrigerant, we are far into this superheat territory. So that means that the system, as we shed heat from the refrigerant across the condenser to the air, it has to shed more heat energy before it can convert from a gas back to a liquid. So again, the significance of what's drawn against the bell curve here for a low charge is that there's a significant increase in superheat. In other words, outside of the bell curve to the right, it sticks out really far. And the evaporator line that we see here, the temperature across the evaporator is really, really low. It's below freezing, and we have poor system performance. So these are good indicators that the system requires a charge. So the system is now fully charged and supposedly operating correctly, but now we've disabled the cooling fan at the condenser. So let's take a look at the bell curve chart now, the enthalpy chart, and see what it reflects for us. Now, as you can see here, the temperature of the refrigerant entering the compressor is above freezing, about 33 degrees Fahrenheit, keeping us close to the bell curve, but still in the superheat zone, just as we desired. However, as we compress the refrigerant and pressure begins to build, since we can't shed heat across the condenser, our head pressure has reached over 300 pounds per square inch and pushing us further and further away from this bell curve. However, the condenser can still shed heat and bring us into the subcooling state we see here. And pressure drop across the restriction is good, bringing our temperature to, again, around 33 degrees Fahrenheit, entering the evaporator. And we have good heat absorption here across the evaporator. So is this system working? Absolutely. The system's working. And the customer at this point probably doesn't even really have a complaint because there's no detectable loss in performance. But this refrigerant loop enthalpy chart shows us that this system is working very hard to achieve desirable results. So now I want to show where this enthalpy chart really shines. How about this first scenario? We've got a vehicle that is in the shop with a stuck blend door, and we've proven that it's a stuck blend door. The question becomes, if I, as the customer, invest the money to repair the stuck blend door, is my HVAC system in good condition? Meaning, do I have a secondary problem? Is my compressor beginning to fail? Is it not pumping correctly? Is there a leak in the system? Is there enough refrigerant in the system? Is the system perhaps airbound or contaminated in some way, shape, or form? Might I have a stuck expansion valve? And things of that nature. Or is there a restriction somewhere? There's no way of knowing this. We would have to first fix the blend door, the temperature blend door issue, and then reevaluate the system. So running a performance test like we read about in the service manual wouldn't really be applicable because we wouldn't even be able to achieve the desirable running conditions to evaluate the performance of the HVAC system. This is where we kind of get stuck at times. But take a look how this enthalpy chart will allow us to evaluate the performance of the refrigerant loop, even though the performance of the HVAC system in its entirety is not up to par. So what we have here, this enthalpy chart, are plotted points, represent refrigerant temperature entering the evaporator at about 32 degrees Fahrenheit, just about freezing, which is excellent. This will absorb heat and become a saturated gas, as we see, stepping to the right of the bell curve as saturated gas entering the compressor. The compressor will discharge the pressurized refrigerant, this case at a pressure of just under 200 psi, and we are still within 2 blue lines of our bell curve, meaning our superheat is just where we want it to be. Our condenser is able to shed enough heat to take us back just outside the bell curve to the left to our subcooling point, to a fully saturated liquid. And our pressure drop across our stricture takes us from 200 psi down to about 45 psi. And the process repeats itself. So looking at this, what do you say about the performance of our refrigerant loop? It says our refrigerant loop is performing just fine, meaning the symptom of hot air conditioning, 133 degrees Fahrenheit blowing out the vents, has nothing to do with the refrigerant loop at all. It's simply a blend door issue. It's a plumbing issue. And if we fix that plumbing issue, we should have good performance from our refrigerant loop. So as time goes by and new technologies are developed, our efficiency of our HVAC systems have become more and more important. And the slightest loss in refrigerant or the slightest problem in heat exchange will cause a significant loss in HVAC system performance as a whole. And for us as technicians who have a job in efficiently and accurately solving problems, it's not a hobby, meaning we can't take forever to find out a problem with a car, specifically an HVAC system in this case. We need tried and true tests that we can apply and leverage with confidence. And in many cases, employing the use of an enthalpy chart can save you time. So practice on known good vehicles. Leverage this as a tool so you can begin to understand what good looks like. So when you recognize a good enthalpy chart plot, bad will stick out like a sore thumb. My friends, with that, I thank you for joining me on this episode of Mastering Diagnostics. I'm Brandon Steckler, Technical Editor of Motor Age Magazine, and we will see you on the next one. Take care.